About a month ago, I got an email from one of my viewers, Victor from Canada. He sent me this image and he was wondering if I could help him to solve this geometry problem. So the catch is that in his book, the solution was given in terms of integrals and trigonometry. But since he is not really keen of those, he was wondering if I could do this without using trigonometry or integrals. So thank you, Victor, for this wonderful problem, and we're going to get right to it. But before that, I just want you guys to notice this do not scale sign. I was first wondering why this sign is even here, but after working through this problem, I found out that this image is actually completely out of scale in terms of angles. Of course, this is not going to stop us to solve this problem, but just keep that in mind. So I will first do my best to replicate this image. So we have the right angle triangle with the legs of 3 plus 2 root 3 and 2 plus root 3. Then we have a circle which has the center on the right leg of our triangle. And basically from this circle, you only need the left half of the circle, which is inscribed inside the triangle. The right part is completely unnecessary. The question is, can we find this red shaded area? And again, let me repeat, do not scale this because trust me, it is completely out of scale. Alright, so you guys can pause the video right now if you want to try this one out for yourself and then come back and check the solution. So let's solve this one. First, I'm going to get rid of the right part of our circle since we do not need it. Then I'm going to label all the vertices of our triangle as A, B, and C and the center of our circle as O. Then let's calculate the hypotenuse of our triangle by using the Pythagorean theorem. We can substitute our values from the sketch and then we can use the square of binomial to expand this. Afterwards, we will simplify by adding the common terms, and we will get that our hypotenuse AC is equal to square root of 28 plus 16 root 3. Of course, this looks absolutely horrible, but fortunately, we have the way to deal with this. We can use one really interesting de-nesting formula, which I really love, which looks something like this. But of course, in order to use this formula, you need our second term inside the square root to be inside the square root of its own. So we will just put 16 underneath the small square root and we will get the following. So here you can see that A has the value of 28 and B has the value of 768. So we're going to substitute those values into our de-nesting formula. Then we will simplify things underneath the small square root and get the following. Now, the first root is actually 28 plus 4 over 2, which is 32 over 2, so that is square root of 16. And the second root is 28 minus 4, which is 24 over 2, and that is square root of 12. Of course, this can be easily simplified as 4 plus 2 root 3, and this is the length of our hypotenuse. Alright, now let's label the radius of our semicircle as r, and let's rotate this radius to the point of contact with the hypotenuse AC, and let's label this point as D. We know that the angle at the point D must be the right angle. We know this by using tangent of a circle theorem, which states that if we have a circle and the tangent, and we pull the radius to the point of tangency, this radius will always be perpendicular to the tangent. And this is of course exactly our case on the left, because as you can see, the line AC is a tangent to our semicircle. Now, let's pay attention to the line OC. You can see that this line is nothing but the difference between the line BC and the radius of our circle, so we can write it down as 2 plus root 3 minus r. Now let's find some similar triangles. First, let's take a look at the triangle ABC, and let's isolate this triangle. Then let's take a look at the triangle OCD. And let's isolate this one as well and rearrange the orientation so it is the same as the orientation of the triangle ABC. Now you can notice that both of those triangles are right-angled triangles, and they also share the same acute angle at the point C. This means that their third angle must be the same as well, which means that those two triangles are actually similar. So now we can use the height and the hypotenuse of those two triangles. And we can form the rule of similarity, which states that the relation between their hypotenuse must be equal to the relation between their heights. And if we substitute our values, we will get this following equation. Now we can solve this equation by first cross-multiply this and get the following. Then we can expand by multiplication. Then we will put all the terms with r on the left side and all terms without r on the right and simplify. Then on the left side we can isolate r as a common factor, and finally we will get that the radius of our circle is 12 plus 7 root 3 over 7 plus 4 root 3. Of course, this still looks horrible, so we're just going to rationalize this. Then on a numerator, we're just going to multiply everything, and in denominator, you can see that we have the difference of squares. So we can simplify 84 first and get square root of 3 over 49 minus 48, which means that the radius of our circle is equal to square root of 3. And I will replace all the values of r for square root of 3. Now, let's take a look at the line OC once more. You can see that it is equal to 2 plus square root of 3 minus square root of 3, which means that this length is equal to 2. Alright, this is great. Now, let's take a look at the line DC. We can find this line as a difference between line AC and AD. But how can we find out the length of the line AD? Well, we can use another circle theorem, which states that the length of tangents from an external point to a circle are equal. So, if I label all the points on the right same as the points on the left, you can see that the line AB and AD will have the same length. So this means that line AD also has the length of 3 plus 2 square root of 3. So now we can easily find the line DC as the difference between the lines AC and AD, and if you substitute our values and simplify 2 root 3, you will get that the line DC has the length of 1. Alright, so at this point, I would probably use a trigonometry, but we can cheat a little bit and we can take a look at the triangle DOC. You can see that this is a right-angled triangle which has the sides in a proportion of 1 to square root of 3 to 2. So this triangle is actually a really famous right-angled triangle which represents the half of the equilateral triangle. So this means that this triangle has the angles of 60 degrees and 30 degrees. And if you take a look at our sketch, you can see that 30 degrees is located between two lines which are in 2 to square root of 3 relation. And those two lines on our sketch are lines DO and OC, which means that the angle at the point O must be 30-degree angle. Now you can probably see why this sketch is out of scale. But it's okay, it doesn't really matter for us. Now we have everything that we need in order to find our red shaded area, and we can find it as the difference between the area of our triangle and the area of the circular sector. So our right angle triangle will have the legs of 1 and square root of 3, and our circular sector will have the radius of square root of 3 and the central angle of 30 degrees. So our red area is equal to the area of the right angle triangle, which we can find as the half of the product of its legs, minus the area of the circular sector, which we can find as the central angle times radius squared pi over 360 degrees. Of course, we can simplify 30 and 360, and also simplify the square root of 3 squared to get 3. Then we can simplify 3 and 12 and get the following. Now we can join those by using the common denominator, and we will get that our area is equal to 2 root 3 minus pi over 4. Of course, if you don't like this, you can approximate it to 0.08. So those are our solutions. So I really hope you enjoyed this problem. If you did, do not hesitate to leave a like or subscribe to the channel. Those stuff really means a lot. Of course, if you found another way to solve this problem, please write it down in the comment section. I always love to see when community finds another ways to solve the same problem. So, until next time, as always, see you guys and take care.